This video describes how to build your own Coolant Mister with one major advantage. It won't create a cloud of mist that fills your workshop and lungs. To start, let's take a look at the options you have as a home machinist for coolant systems. There are two main types of coolant for CNC machines, flood and mist. Flood looks a lot like a fire hose. So what should you think about if you're considering flood coolant? Firstly, it's higher cost. It works best for very large stock removal. It tends to be messy and it needs containment. Soluble oils in a tank tend to have issues with mold and other growths. Flood coolant is somewhat tough for home machinists to manage. Then there's mist, which looks a lot like an aerosol spray can output. Some considerations about mist. Firstly, it's lower cost. It's good for moderate stock removal and definitely generates less mess. Containment requirements for mist are less, and sometimes you can get away with none at all. Frequently, this is seen as the best choice for home machinists, but coolant mist clouds are a major hazard. So, when we talk about mist, what are we looking at? This is a freeze frame of what happens when you use an aerosol, in this case, a spray can. A cloud of droplets are propelled from the nozzle, generally in a forward direction. Anyone who has used a spray gun knows how far the overspray is going to travel and how much you need to have fans and filters to maintain a clean environment. And even then, you should be wearing a high-efficiency filter mask. This diagram shows how the discharge from a spray nozzle actually works. The stream of liquid is propelled only a short distance before it progressively breaks up into finer and finer droplets, losing momentum, fanning out, and eventually fogging the room, much like a roach bomb. To protect machinists, industry deployments where coolant mist is used utilize mist filtration systems. Way too expensive for a home CNC machine shop. The folks at fogbuster came up with an awesome solution for home machinists. fogbuster delivers a spray of coolant to the work plus air pressure to remove the chips, but all of this without creating a fog of mist. Take a look at fogbuster.com, and if you can afford one and it suits your build, please buy a fogbuster from them. Strictly, the fogbuster works by delivering a stream of coolant drops that are contained inside an airstream. It turns out that all of that fluid dynamics I learned at university proved useful. However, unlike conventional misters, the coolant is not aerosolized, so there is no fog to fill the room. The fogbuster patent was filed about 30 years ago and describes in great detail the design elements needed to achieve their successful outcomes. The patent expired 10 years ago, so the patent contents is in the public domain, and the inventor, Lee Hench, provided a wealth of technical information about the necessary conditions for a fogbuster to work. I took the description in the patent and re-engineered my own version that is a different layout but still meets the essential requirements. So of course, it was obvious that it had to be named the Mistbuster. The patent is not very long, but these are the key design elements. The nozzle is a rigid structure with a length of 5 to 6 inches. For most of that length, the optimal inside diameter of the nozzle is 93 thousandths of an inch. For the last 3/4 of an inch, the inside diameter drops down to 47 thousandths of an inch. The manifold or mixing chamber for the air and coolant needs to be rigid and preferably made of metal. Although at the air pressures involved, it could be made of plastic, assuming that it will be non-reactive to the coolant. The valve stem to control the coolant admittance must be conical. Two of the key elements in the design are that the air and coolant are pressurized to the same amount and that the working pressure is maintained between 10 and 30 psi. In general, the system seems to work best at the lower end of that pressure range. I designed the prototype in Fusion 360, looking to keep the machining requirements for the sprayer as simple as possible within the design constraints. Let me know in the comments if you would like a copy of the prints. This is the Eclectic Builds channel, so of course the first few iterations of the prototype were built using a 3D printer. Although some of the intended components, like the pipe fitting for the air and coolant delivery tubes and the set screw, were tested using off-the-shelf components. It turned out pretty well after only 3 iterations, with most variations concerning the mixing chamber and the size of the valve stem. For the rest of the components, I purchased an enclosure to keep everything neat, a coolant reservoir, and then some miscellaneous items like an air control solenoid, polyurethane tubing, an air pressure regulator, and non-return valves. The metal stock I purchased was aluminum bar, long enough to make about a dozen sprayer bodies, and I lucked out finding brass tubing. Trying to drill a hole 93 thousandths of an inch in diameter and 6 inches deep was a bit more than my shop can manage. I found some thick wall brass tubing that had an inside diameter of 90 thousandths of an inch, which is about 3.5 thou smaller than I needed, but so close it doesn't count, especially given that the end of the sprayer meets the final inside diameter requirements. The next build video in the series looks at machining the MystBuster sprayer, and the one after that will show how the rest of the coolant system was constructed and tested. Finally, this is what the sprayer looks like mounted on a magnetic base on my CNC mill. Thanks for joining me on the theory and design requirements for this build. The actual build stuff is coming up soon.